This episode is sponsored by Brilliant. Geoffrey Chaucer said that all good things must come to an end, but this channel is not the place for that kind of pessimism. So today we'll be discussing ways we might postpone the heat death of the universe, and possibly even delay it entirely. To do that, we must first discuss what the heat death is and why we think it's going to happen. The best place to begin is to note that there is a bit of a difference between what we normally think of as heat and what the term means in physics. Heat, to us, in a casual and day-to-day sense, is how warm it is. But in a physics and thermodynamic sense, it refers more to how entropic a system is, essentially what portion of its total energy is heat energy. Heat is random motion of particles, and we can only get work done using such a system if it's got other energy still stored in it in other ways, or if we connect it to something colder. As an example, the sun is very hot, so we can easily get work done off it by connecting to something cooler, which we obviously have plenty of choices for. It is making that heat by converting hydrogen into helium, photons, and neutrinos, converting mass energy into heat energy in the process. A system is at maximum entropy when all those options have been used up and everything is converted to heat that can be, hence heat death. It's a bit confusing though, since we'd expect this to happen nowadays when it's rather cold, but beyond that term really meaning maximum entropy, we should keep in mind that our cosmological models have changed over time. As an example, we often talk about how you can't hide a megastructure like a Dyson sphere because it needs to radiate away all the heat it's been absorbing from its own star or get cooked. And when we think of space as cold, it's easier to forget that not only is it not cold, but most of the mass in our solar system, for instance, is blazing hot. There is very little heat as heat energy in empty space, but that's not temperature. The temperature of outer space near Earth is about 283 Kelvin, a temperature of 10 Celsius or 50 Fahrenheit, light jacket weather. There's just virtually no particles around actually containing heat in a near vacuum, but those that are around are warm enough. Alternatively, 98% of the solar system's mass is inside the sun and boiling hot, and half the remainder is in Jupiter and quite hot too. We used to think we lived in a steady state universe, one which does not expand, or is infinite but basically homogeneous. Go anywhere and find about the same density of stars, all bits more or less the same. In such a universe, a heat death can be pretty literal. All the mass energy that can be converted to heat eventually does get converted, as even photons made in this process eventually get absorbed somewhere, and even those emitted as heat radiation by warm objects will just get absorbed somewhere else down the road. Your whole universe turns into warm objects bathed in a flood of photons of about that temperature's black body wavelength. We've not discussed Bohrs paradox in detail here before, mostly because it's not a paradox anymore under new cosmology, but you can look that up if you want details on this notion. Short form, in a static and non-expanding infinite universe, you have a star in every direction you can look, so the sky is bright white, not mostly black, and everything gets real hot. This is even true in a universe that isn't infinite in size or age too, if it isn't expanding. And in such a universe, a heat death is quite literal in the normal meaning of hot too. Alternative cosmologies like the Big Rip also circumvent our normal concept of a heat death too, though by killing everyone on a shorter timeline. It's only in an expanding universe that our particular form of heat death can occur, be that universe finite or infinite, because it means the total volume of space is constantly on the rise. And yes, an infinitely large object can keep growing even though infinity plus infinity is still infinity. Infinity is not a number. The size of a universe doesn't matter for this purpose, just that it keeps expanding and thus eventually you get distances big enough that the expansion rate between galaxies is faster than light can catch up to. That's what lets us get around Bohrs paradox, and why the cosmic microwave background radiation, or CMB radiation, which is leftover light from when the universe was younger and hotter, is redshifted all the way down to chilly microwaves. Originally, when those photons were first emitted, they were mostly visible and high infrared. If the universe weren't expanding constantly, we'd be bathed in those original photons at their original energy. It has been suggested that if we could somehow stop dark energy and stop the universe expanding, we could stop the heat death, but quite to the contrary, that would actually kill us faster. We can keep extracting warp from matter only as long as we have some cooler places to move that heat, and if expansion ends, everything would just start warming up because none of those emitted waste heat photons would have anywhere to go but other bits of matter they eventually ran into. Everything would also start falling back together into a big clump, unless the universe was actually infinite, so that stuff was pulling equally strongly with gravity in every direction, and even then you get a lot of local clumping ending in giant black holes everywhere eventually. Had this expansion stopped back when the universe was smaller and that CMB radiation first emitted itself, around the year 300,000 ABB after a Big Bang, the universe would be 1,000th its current size and about 3,000 Kelvin everywhere and bathed in photons of about that frequency. Instead, that expansion is fast enough that everything is on average cooling down. Regardless of whether or not the expansion of the universe is accelerating, and whether or not that acceleration is a good thing, that expansion itself is a very good thing for us, both that it was expanding and that it continues to expand. A quick note on that idea, that you can't travel faster than light, but that these galaxies are separating faster than light, which obviously confuses people. First, it's not that stuff can't go faster than light, a shadow for instance can. Rather, it's that information and cause and effect can't go faster than a certain speed, and that objects with no mass happen to move at that speed, such as photons of light and presumably gravitons, and we just happen to discover photons first and name that speed the speed of light. Second, those objects aren't exactly moving away in a classic sense. Everywhere in the universe, little pockets of new space are popping into existence, presumably very, very, very tiny bits of space, probably Planck volumes, a space so small it makes atoms seem galactic in scope, and probably appearing inside you and me this very moment. Locally, this is irrelevant because all those normal forces binding matter together easily compensate for that, though in a big rip universe, the rate at which these new bits of space pop into existence keeps increasing until they start popping up so fast and numerous that even electromagnetic forces binding your molecules together can't yank them together fast enough to keep you together. Right now it's slow enough that even gravity, the weakest force in nature, though the only one that meaningfully functions at galactic scales, can keep galaxies together and with their nearest neighbors too. Above this scale, all those little new pockets of space add up to so many that the new bits of space between two objects are emerging quicker than the light between them can cover. So photons or gravitons emitted by those objects never reach the other object. Those galaxies are moving away from each other faster than light, but because new space is popping up between them faster than light can cover. This can be confusing because we believe the vast majority of the actual universe is already beyond this point and more gets added every day, moving away from us faster than light. We then turn around and tell people nothing can move faster than light, even though virtually all the matter in the universe is moving away from us faster than light. It can be a bit perplexing. In any event, we know what this cosmological future holds for us, more or less. The universe expands and every galaxy merges with any nearby neighbors into slightly larger galaxies that get left as islands in a locally empty universe. In a couple hundred billion years, all the universe we can really see, except as redshifted galaxy ghosts, will be our big new merged galaxy about an order of magnitude more massive than currently, and various isolated small stars and clusters that were moving away from us a bit too fast to get yanked into that merger, but not yet shoved far enough away by expansion to have disappeared. Like a big continent with islands and archipelagos of stars drifting further away. All those other galaxies we can see now will be off and gone and in their own dark pockets of space, each considerably bigger than the current observable universe. Emphasis on observable universe because most of the universe is presumably already further away from us than we can see over the cosmological horizon, as we explained a moment ago. This is not the heat death of the universe, star formation will have slowed a bit by then, but as far off as that date is, around 10 times the age of our current universe, star formation won't significantly slow for considerably longer, and shouldn't start heavily ebbing off for at least 10 times longer than when this period begins. Indeed, most of the stars alive nowadays will still be alive then. Our sun may only have a lifespan of 10 billion years, and will be getting ready to enter its death throes when our final galactic merger begins. but our star is on the big and short-lived side. Most stars are red dwarfs and live hundreds of billions or even trillions of years. Indeed, while we might then say our universe at this point is a big empty one far larger than in the present day and centered on a conglomerated large galaxy, our universe is pretty debatable. We probably can build ships fast enough to have caught up to those fleeing galaxies before they got too far away and too fast to catch. However, for those folks still living in our galaxy at this point, or its larger merged form, we'll have to say goodbye to our cousins who made that voyage by this point, or any alien civilizations that arose in them and that we'd struck up conversations with, unless we discovered actual faster light travel by then. And if it's possible, I'm sure we would have, as 100 billion years is a lot of time to do research, especially with galaxies worth of colonies to add their efforts to that research. For my part, I don't expect we will ever get a workaround to light speed, but many such technologies offer their own options for postponing the heat death, and we'll get to those shortly. First, let's finish up the forward progress to the heat death. It will take a long time, but those stars will eventually stop forming as often and dying off and will go dark, a universe of random gas floating around dead suns and slowly drifting apart or falling into black holes. Whatever mass remains cannot be used to extract more work. Now, in an inhabited universe, folks have probably stockpiled lots of mass they can feed into fusion reactors or make new suns with, but that will run out eventually. They can also feed that matter into black holes and extract energy that way. See Colonizing Black Holes for details on that. And indeed, they might help supersize our local galactic merger by even shoving slightly more distant galaxies together, as we looked at in Fleet of Stars. But in the end, everything is either too scattered out to reach or in those black holes, and this is the default end of the universe. As we discussed in Civilizations at the End of Time, even once all that matter is down in those black holes, they are thought to slowly decay and give off radiation, and you can theoretically live off that. Since the universe is going to keep expanding and cooling, those black holes should all eventually evaporate too. Right now, they don't lose mass even when they've no matter nearby to suck in because of that CMB radiation. It's everywhere, and as thin and weak as it is, it's still stronger than the Hawking radiation emissions of even the most powerful natural black holes, so they emit a little bit of Hawking radiation but suck in more CMB radiation and grow in mass from that alone. As that weakens and thins out, as we expand, they'll start hitting tipping points where more comes out than goes in, and less massive black holes emit Hawking radiation faster, and emit it ever faster and more powerfully as they shed mass. Eventually, any black hole will have reduced in size to something emitting enough power you can usefully collect energy off it. Hawking radiation off a natural black hole, for instance, couldn't even power a light bulb continuously, even if it emits insane amounts of energy, just because it does it so slowly. Capturing that energy and maintaining the equipment that does it over timelines of trillions of years is no easy challenge, and indeed might be impossible, whereas gathering power off a black hole by dumping matter into it is actually quite easy. See the Black Hole series for details. But they generate far more power as they evaporate and shrink in mass. One that shrunk to about 20 billion tons of mass would be giving off a megawatt of power, and would continue to do so for a couple billion years, slowly rising in power as it did this. A civilization could carefully add set amounts of matter to black holes, getting power as they dropped mass down into them, but cutting off the flow when they hit a certain mass on each, and measure a bunch of them up to slightly differing masses to stagger their lifetimes out so they were giving off useful amounts of energy one after the other in series. Of course, useful depends on your technology and your nature too. As we discussed in Black Hole Farming, a post-biological civilization living as uploaded minds should take way less energy to run a mind on a computer than biology does, potentially billions of times less, and thus might be able to run a pretty massive digital civilization on something like a single megawatt black hole power plant. However, the universe does cool, and the theoretical minimum amount of energy needed to flip a bit on a computer, or several to produce a digital person's thought, is proportional to the switch's temperature. We call this the Landauer limit, and in a cooling universe it means you get way more computational bang for your buck. you can do 10 times the calculation with the same energy at 1/10 the temperature, or 1,000,000 times the computation at 1,000,000th of the temperature. Again, see black hole farming for further discussion. That of course merely postpones things for civilization, though in a massive way, and either by staggering your black hole masses, or getting more effective at quarter computation, or both, you can keep this running for trillions of trillions of trillions of trillions of trillions of trillions of years. Indeed, if proton decay doesn't occur, and we have little evidence to indicate it does, you might be able to survive this way to the end of the black hole era, and maybe even stretch things out to the iron star era somehow, a period of time so far in the future that it makes even the black hole era look like an eye blink of time, and that era is already so long that it likewise makes the entire period of the universe stars would occur in look like an eye blink. That's a pretty good postponing of things, and none of it requires any new physics, though for much of it you need some beyond impressive improvements in engineering to take full advantage of it. Though the staggered black hole mass trick requires only the ability to make black holes less massive than stars, and we ought to be able to do that using some of the techniques we discussed in our black hole series. Even if you can't make black holes less massive than a large asteroid by imploding giant balls of iron wrapped in nukes, which should be doable, such things should be short enough lived we could huddle around reserve power sources or trickle-feeding mass to other natural black holes till they started expiring and giving off useful amounts of power. This is nothing like the great and glorious digital period that a post-biological civilization that's mastered artificial micro-black hole generation could enjoy, but it would allow at least some remnant on par with modern population numbers to dwell on for ridiculously long periods of time under known physics. But let's start considering some options for unknown physics. I mentioned faster-than-light travel earlier as a workaround to the heat death, and one of those methods is that FTL is usually the same thing as time travel, and as we mentioned some weeks back in our time travel episode, you can always jump back in time to an earlier period of your universe, or possibly a different universe, and escape the heat death that way. Needless to say, any technologies that permitted travel to newer or younger universes, assuming they exist, also allows this option, and not just for escaping either. Entropy or heat death is what happens when a system runs out of available work energy in a closed system. You can always add more energy from outside, or connect that system to another system that's colder and run a heat engine between them till they reach equilibrium. So if you can travel to new universes or dimensions and travel back and forth, you can postpone the heat death of our universe that way. You just open a gateway to a younger or lower entry place, or one where that concept doesn't even apply. We don't want to assume the sum total of reality is merely different variations on the events and age of our own, but with the same rules. After all, there was always that irritating question of where all the energy in this universe came from initially, and where all that dark energy came from. And as a side note, while some folks in cosmology like to occasionally suggest it might not need to have come from anywhere, and while that is presumably possible, there's nothing even vaguely scientific about that claim at this time. We know nothing more of what comes before or outside this universe than we knew back in the time of folks like Plato and Socrates, with the exception of having a bit clearer view on how space and time are merged together and run. And while I entirely sympathize with a lot of cosmologists and theorists wanting to weave that into our current models, it's all very hand-wavy and maybe a bit irresponsible. Time in this universe doesn't have to have had a beginning, and presumably doesn't have a 0-1 moment, but that does not just let you say cause and effect at a grander scale do not exist. Of course it might not, we just don't know, but critically, we don't even have a hint of the tiniest clue at the moment, scientifically speaking. That's not just me poking at theorists for speculating on a lot of stuff without evidence to back it up, but also a warning since we'll be doing that ourselves for the remainder of the episode. From this point on, while we'll be sticking to concepts with at least a decent theoretical framework behind them, we are moving outside known science or strong theory, so grain of salt, or dump truck of salt perhaps. First, it's always possible that expansion of the universe is not an eternal thing, and eventually dries up into a non-expanding or steady state one. or that the broader multiverse or whole grand shebang is effectively steady state, and all those other universes and realities you might be mining for energy would dry up too. However, such a case leaves the door open for a random reset, what we call a Poincare occurrence. Shuffle a deck of cards enough times, and it will eventually return to the order it was originally in. Take anything random and changing, and it will eventually repeat states, and when we're discussing it in entropic terms, it need not perfectly reset either. A deck of cards will return to its original state, but along the way it will form a lot of patterns, like having several cards in a row be in numerical order, or lower entropy so to speak. The amount of time involved for this to happen, even for a simple deck of cards, 52 objects in 52 possible states each, are simply enormous, and grow vastly more enormous for each element and possible state added. However, the bigger your deck, the more small patterns, or randomly lower entropy spots you'd have emerging. If you could find and access those in our analogous universe, you could presumably run a civilization off them indefinitely. But all that assumes you can't either reverse entropy in some deliberate fashion, or create reversible processes. It may be possible to do reversible computing, cases where you can flip, unflip, and reflip bits without expending any net energy or raising entropy. However, from a practical standpoint, it's rather debatable if this really allows true and lasting computation in the context of thought and memory, since you're arguably undoing the computation or thought when you reverse it. And of course you always get some loss around the edges on any system, so reversible computing might only allow a postponement of entropy rather than a standstill or reversal. The same will generally be true for any reversible process besides computation too. Can you reverse entropy though, break the laws of thermodynamics, turn back the growing chaos of a system without doing so by adding more chaos to another system? We don't know for sure of course, and folks have often suggested ways to do it, or even claim to have accomplished it, and not simply random loons or scam artists offering perpetual motion machines. Back in 2016, researchers at Argonne National Labs came up with a way we might be able to do negative entropy gain at a local, temporary, and quantum way, and quantum does seem to offer us some avenues that might permit local entropy drops. This does not necessarily mean they actually do, or that such a thing could ever be scaled up to macroscopic scale. Taking advantage of quantum behavior by simply scaling it up, or building huge numbers of copies of it does not generally work, or at least is insanely more difficult than folks tend to assume. Though I'm not too pessimistic about such avenues. Most of our theoretical notions for where all the stuff for the Big Bang might have originated from usually do tie into quantum, where stuff can just appear out of nowhere anyway. Although let me caveat that by saying we just tend to say appear out of nowhere. We don't know if it does any such thing, and use the phrase to mean we don't know where from, possibly from nothing at all, rather than yes, this definitely appeared from nothing at all. It's problematic when discussing how to escape or delay the death of the universe when you don't know where it came from or what the underlying quantum structure is, beyond that there seems to be one, and it seems to constantly foam and froth with vast amounts of hazy potential particles and energies. If we could learn to tap those, basically the concept behind vacuum energy, then that might let us get around the heat death too, though maybe not since they seem by their nature to be random and it's not possible to get work done from randomness. That's basically the notion behind the laws of thermodynamics in the first place. Of course, playing around with that, if we ever start figuring out how to and assuming it's actually possible, might change our outlook on the matter. Amusingly, if darkly so, it might also have the opposite effect of postponing the end of all things. There's a bit of a concern that if you poked around at that stuff, you might effectively poke around at the bottom of the universe and metaphorically drain it away, and you've probably heard of the notion of the false vacuum. The universe is mostly empty space, but not quite a true vacuum. Little bits float around in it, and any given bit of it has photons, such as CMB radiation, passing through it. But even if you remove those, create a true vacuum, it still isn't one. It also has vacuum fluctuations, little bits of things popping in and out of existence at the quantum scale, a false vacuum, not quite the lowest possible state of energy. We've some reasons to worry you could accidentally poke this, or that vacuum decay might happen naturally, so space in a spot did drop to a true lowest state, and that this lowest state would then begin expanding at the speed of light in every direction, basically wrecking the universe in an expanding bubble of true nothing. Such a thing might already have happened somewhere in the universe, naturally or in some alien lab, and be working its way here even now. Or of course have happened in some prior iteration of the universe, and our universe resulted from that cataclysm. That's an amusing answer to the Fermi Paradox, where all the aliens are at in this huge and ancient universe, since so long as we don't assume intelligent civilizations are too common, not more often than once per galaxy every few billion years, this might account for their absence. They figure out how to access this false vacuum and accidentally ignite a vacuum decay, which spreads out at light speed, eating their planet, and even catching up to any of their colonies and slower than light ships. Only their early and weak signals would perceive this catastrophe to anyone out there listening, so they probably missed the signal, and regardless, even if they heard it, would only have a short time before vacuum decay reached them anyway. Or that every civilization that first emerges in a universe eliminates themselves and everyone else by doing this. It's not really a Fermi Paradox solution you need in a no FTL universe, but it works for ones in which FTL travel is assumed to be possible, since it offers you a way to kill off those species before they discover how, and removes the problem to the Fermi Paradox of having to deal with the absence of aliens if we have to include ones spawned in far distant galaxies, including those over the cosmological horizon. Though perhaps not, since vacuum decay happens at light speed and expansion can occur faster than that. However, while it's often noted that anything useful for bettering our lives can be made into a weapon, the reverse is also usually true. Your swords can be turned into plowshares, so potentially such a cataclysmic option like vacuum decay might be in some way usable as a controlled power source too. We don't know how to mess with that false vacuum yet, assuming it even exists or exists as we think it does anyway. But the ability to mess with it implies a potential ability to manipulate or contain it, and that could open the door to flat out making new bits of matter and energy, or even whole new universes. For my part, I think that's a much more interesting Fermi Paradox solution, that folks learn how to play around with stuff to make new matter, energy, or space-time, and finding it better and easier to pursue that option for expanding their civilization, as opposed to building giant slow generation ships to colonize new worlds. The heat death of the universe, and postponing or reversing or evading it, ought to be the top priority for any advanced civilization. And to end the episode on a hopeful note, since that would be the grand work of any ancient and vast civilization, an alternative to us not seeing ancient alien empires all over the universe might not be that they simply don't exist, but rather that they solve the whole problem of finite resources in an entropic and decaying universe, and thus had no need to venture far out from their homeworld to find new resources to let them expand into, to grow, or stockpile against the grinding engine of entropy. If they did, then that means that we can too, and all good things don't have to come to an end. As we mentioned, the fundamental concept of the heat death of the universe is all about statistics, entropy, and the laws of thermodynamics. If you're interested in learning more about those, and other statistical concepts, I'd recommend the quizzes on thermodynamics in Brilliant's Classic Mechanics course, or their Statistics Fundamentals course, with over 24 interactive quizzes that will help you master statistics, one of the most valuable areas of math and reasoning to know. Brilliant is an online learning community with over 60 interactive courses and many quizzes and puzzles, plus daily challenges that help get the brain warmed up for the day. Those challenges provide a context and framework that you need to tackle so that you learn the concepts by applying them, which is the best way to learn new concepts. Brilliant makes learning fun and easier, and their online community gives you places to discuss the material or ask questions, and their mobile app's offline feature lets you take courses even when you're not getting a good signal. If you'd like to learn more science, math, and computer science, go to brilliant.org/IsaacArthur and sign up for free. And also, the first 200 people that go to that link will get 20% off the annual premium subscription, so you can solve all the daily challenges in the archives and access dozens of problem-solving courses. So today we were talking about potential distant future calamities like heat death and vacuum catastrophes, and next week we'll be looking at ways to fix or mitigate catastrophes a bit closer to home in both space and time, in climate change mitigation, where we'll explore what options we have now or in the near future for everything from greenhouse gases to volcanoes and asteroid impacts that might mess with our planet's thermostat. We also discussed some post-human civilizations in passing today that might live around black holes one day, and in 2 weeks we'll look at something similar but also sooner on the horizon, as we discuss DNA manipulation in living subjects. For alerts when those and other episodes come out, make sure to subscribe to the channel and hit the notifications bell. And if you enjoyed this episode, hit the like button and share it with others. And if you'd like to support future episodes, visit our website, isaacarthur.net, to donate to the channel or check out some of the awesome SFIA merchandise. Until next time, thanks for watching and have a great week.